Greetings from Group 2. Our topic of discussion is hydrocracking of vacuum distillates to produce gasoline and other fuels. First, let me introduce our team. My name is Iming Chuan with matrix ID of 16002836. My task in the group is to do introduction and catalyst screening. Other members are Wang Xianwan, Chu Qinhua, and Temen Chi. Wang is in charge of reaction mechanisms and summary, Chu takes charge of determination of basis for reactor design, and Te completes the reactor selection and design. Hydrocracking is the process of cracking heavy molecules into distillate and gasoline in the presence of hydrogen and a catalyst under high pressure and temperature. Vacuum gas oil from vacuum distillation unit are sent to hydrocracking units such as fluidized catalytic cracking (FCC) or hydrocracker to be upgraded into light products, which can be further categorized by light and middle distillates. Hydrocracking is a two-stage process that combines catalytic cracking and hydrogenation. Catalytic cracking breaks down high boiling aromatic stocks to produce lower molecular weight with a higher hydrogen content product. Hence, products with lower yield of coke can be produced. Hydrogenation uses hydrogen to stabilize the reactive fragments produced during the cracking, thereby decreasing formation of coke. As a result, long on-stream times can be obtained without the necessity of catalyst regeneration. Hydrogenation is also used to control the temperature of the reactor that prevents the reactor temperature from cooling to the point that cracking will not occur and from rising too high that can jeopardize the safety of the operation. One of the advantages of hydrocracking is upgrading low-quality heavy gas oils into high-quality fuels. Besides, a wide range of feedstock, including the byproducts of catalytic cracking, such as light cycle oil, can be processed. Hydrocracking is also highly flexible that can process light and heavy feedstock. In naphtha production, for example, the hydrocracked naphtha is an excellent feedstock for catalytic reforming and yields high-octane number gasoline. Next, I'll explain about catalyst screening. Hydrocracking process is usually performed over acid metal bifunctional catalyst. The cracking activity is controlled mainly by the support that is acidic in nature, whereas the hydrogenation-dehydrogenation activity is due to the metals loaded on the support. Catalyst support in bifunctional catalysts can enhance activity, selectivity, and stability by manipulating the surface properties. For commercial hydrocracking catalysts, only zeolites and amorphous silica alumina are used commercially. From the table, we can see that zeolite-based catalyst has many advantages in terms of activity, stability, regenerability, and resistance to substances that can interfere with catalyst activity. As for ASA, their mesoporous structure can prevent diffusion limitations and it exhibits more moderate acid size compared to the high acidity of zeolites, which will result in catalyst deactivation due to coking. For metal sites, the metal sulfide supported on gamma Al2O3 are generally used. Gamma Al2O3 can promote excellent cracking activity with its high specific surface area, while hydrogenation catalysts like nickel tungsten and nickel molybdenum are widely used because they are cheaper and more resistant to sulfur compounds. Since zeolite-based catalyst has better overall performance, we will further investigate different zeolite catalysts. Nickel molybdenum on beta zeolite has higher activity due to higher concentration of Bronsted acid sites compared to Y zeolite. Despite that, Y zeolite has higher mesopore volume. Its larger mesopores and high acidity promotes the diffusion of VGO and accessibility to the active catalyst sites with improved stability, resulting in higher yield of gasoline with low coke formation. Our choice of catalyst is nickel tungsten supported by gamma Al2O3 with modified Y zeolite support because catalysts containing noble metals on zeolite Y are more sulfur tolerant than those on other supports, with NiW being the most reactive solid for hydrogenation. Modified Y zeolite with optimal zeolite acidity and improved availability of the acid sites performs good cracking activity to produce gasoline. For catalyst performance data, I included results of VGO hydrocracking using Y zeolite, modified Y zeolite crystallite size, and beta zeolite. It can be observed that NiMO on beta zeolite has the highest VGO conversion at 405 degrees Celsius. Next, we can compare the mesopore volume of the mentioned zeolites and modified Y zeolites has the highest mesopore volume. From Figure 2.1 and Table 2.5, we can observe that the gasoline data in terms of lump yield and conversion from different variables.
Now it's my turn to talk about reaction mechanism. The hydrocracking kinetics was studied in a fixed bed reactor over the hydrocracking catalyst A using a first order kinetic scheme involving 4 lumps. After hydrocracking in vacuum distillates, it will produce into diesel, gasolines, followed by gases. Theoretically speaking, the 4-lump kinetic model scheme should include a series of reactions and parallel reactions, but the hydrocracking catalyst A has low cracking activity and rarely takes part in secondary cracking reactions. So only the parallel reactions of heavy oil cracking was considered in the model schemes, while ignoring the secondary reactions, namely the formations of diesel lump to gasoline, the gas lump and gasoline lump to gas lump. We take the following assumptions into considerations. All the reactions are first order and irreversible. Polymerizations and diffusions of the reactants are neglected. The flow state of all reactants is plug flow and the reactors are adiabatic. The velocity is changed along with two reactors. The pressure is fixed, namely the pressure change is neglected. This is our reaction mechanism, A to B plus C plus D. A is vacuum gas oil, B is diesel, C is gasoline, and D is gases. First is the more balanced equations for the fixed bed reactor, followed by the red law is the first order and the stoichiometric equations with no barrier drops that shows at the right side. The epsilon value of 2 that YA0 is equal to 1 and the kita is 3 products minus 1 reactant. By combining 3 of the equations above, we can get the final form of the equations after rearranging. In these equations, the only unknown is K value, so we need to determine the K value. Normally, we will use the first equations to calculate Kij value. But because of 4 lumps, we need to use Kj that denotes the reaction rate constant matrix that combine with the equations of AIM reaction coefficients and Kij rate reactions for 4 lumps to get the value of Kj. Besides that, for the energy balance equations in the reaction mechanism, we will assume adiabatic operations that Q equal to 0 and no work done on the system, Ws equal to 0, that will form the equation above. From the equation above, A denotes as the heat exchanger area per unit volume reactor with the equations area over volume that get 4 over diameter. And the right side, total kita CPI will be only form CPA since only A enters. This is the finalized energy balance equations followed by delta H0 Rx and delta Cp equations for the part of reaction mechanisms.
My name is Jinhua. Now I'm going to present a part 4, which is the determination of basis for reactor design. Table 4.1 shows the main property of the feedstock that is using in our hydrocracking reaction. The feedstock that is using is uranium vacuum gas oil, VGO. It has density of 0.913 gram per cm3 at temperature of 20 degrees Celsius. As we know, vacuum gas oil feedstock consists of multiple hydrocarbon compounds with different carbon number. Each hydrocarbon compound have different boiling point. The initial boiling point of uranium vacuum gas oil is 336 degrees Celsius. For information, initial boiling point (IBP) is the temperature at which the first drop of distillate appear after the commencement of distillation. Because vacuum gas oil consists of different hydrocarbons, therefore it has different distillation point. For example, for 30 to 50% of vacuum gas oil is boiled up at 409 to 433 degrees Celsius. The final boiling point, which is 542 degrees Celsius, the volume mean boiling point of uranium vacuum gas oil is 438 degrees Celsius. Table 4.2 shows the operation condition of our reaction. The reaction is occur at a temperature of 381 to 390 degrees Celsius at pressure of 15.7 megapascal. It has liquid hourly space velocity LHSV of 1.5. LHSV is the ratio of the volume of liquid feed per hour to volume of reactor. 1.5 LHSV, which means for 1 unit volume of reactor, can handle 1.5 unit volume of liquid feed, or the hydrogen to oil ratio is set at 1500. The inlet volumetric flow rate for volume gas oil is 1000 liter per second. Table 4.3 shows the product yield distribution of uranium vacuum gas oil. At temperature 381 degrees Celsius, it has conversion of 65.3% with a gasoline yield of 11.04%, while at 390 degrees Celsius, it has conversion of 83.52% with gasoline yield of 20.83%. The conversion and yield is calculated using the formula as shown. From the histogram, we can observe that vacuum gas oil conversion increase following the increase of reaction temperature. The product yield of gas and gasoline also increase when reaction temperature increasing, while diesel is decreased when temperature is increased.
Based on the catalyst that we had chosen, which is nickel tungsten on gamma alumina oxide with modified white zeolite as support, the most suitable reactor type for hydrocracking reaction is the downflow fixed-bed catalytic reactor, which is operating in trickle flow regime. On the right is a schematic diagram of the downflow reactor, where the feed and hydrogen gas enter from the top and the product exit at the bottom. Thick wall is constructed from special materials to vessel the reactors, and the reactors are usually cylindrical vessels with stabilized austenitic stainless steel for corrosion protection. Since hydrocracking is an exothermic reaction, the reactor temperature has to be controlled. A commonly used commercial hydrocracker consists of several separated catalyst beds. This is because this will be able to manage the heat release with the quenches in between the catalyst bed. In order to control the reaction rate and also to allow safe and steady operation, the fluid exiting one catalyst bed have to be cooled prior to entering the next catalyst bed. Therefore, cold hydrogen gas is injected into the quench zones. Separating catalyst beds using quench zones can achieve the following functions. 1. Cooling of the partial reacted fluids using the hydrogen quench gas, assuring constant temperature distribution of fluids prior to entering the next catalyst bed, mixing efficiently and dispersing evenly of the fluids over the top of next catalyst bed. To remove cold formed upon combustion, ways used for catalyst regenerations are continuous rotor-louvre, porous moving belt as generator, and the ebullated bed technology. Since the catalyst that we had chosen is a metallic compound supported on pelleted alumina, this catalyst can be regenerated in situ with air, steam, or flue gas through a temperature cycle of 400 degrees Celsius to 650 degrees Celsius. On-stream cycles of 4 to 5 months can be obtained at this sulfurization level of 65% to 75%, and the catalyst life can be as long as 2 years. In order to design our reactor, a few assumptions has been made to aid the calculation. Parallel reaction only, where secondary reactions are neglected, equimolar reactant, negligible pressure drop, negligible mass transfer limitations, adiabatic reactor, perfect radial mixing and no axial mixing in temperature, velocity and concentration, and steady state. After completing the detailed calculation, we obtained that the amount of catalyst required for the reactor is 3,232 kg, while the volume of PBr is 5,958.29 liter. The detailed calculations will be appended in the report. On our left is the reactor dimension, where it consists of 4 catalytic bed reactor and 3 quench zones. The height for each catalytic bed is 0.59 meter, while the quench zone is heighted at 0.1 meter each. The radius of the reactor is 0.9 meter, while the total height of our packed bed reactor is 2.66 meter.
For summary and conclusions, we had talked about catalyst screening, reaction mechanisms, determination basis for reactors design, reactor selections, and reactor design for our topics. As conclusions, hydrocracking of vacuum distillates to produce gasoline and other fuels is versatile, flexible, and can be strongly adapted to inferior feed oil with a strong capability to convert the heavy, high boiling, and high end boiling point feedstocks to smaller or lower boiling ones like qualified jet fuel, diesel, and naphtha for chemical use. Thank you for lending me your ears, and thanks for watching.